All right, looks like we're up and running. Hope everybody's doing good on Tuesday. For those in the US, hope you had a great Thanksgiving. Some of you requested some in-depth review of some of the kind of thread and kind of concurrency functionality of Zephyr. So I'm just going to jump through and show kind of my take and probably the more important things you need to take away from all the different types. When it all comes down to it, and you'll see towards the end of this, it's all variants of the same thing. So we'll jump in. It's mostly just slides today, but if you have any questions, just shoot them in the chat, and we will get going. And I'll slide over here. Don't forget to subscribe. It really helps me out. And also, if you leave any comments, let me know what you think. Let me know what you want to learn about. I am open to sharing more about Zephyr and just embedded programming and hardware design in general. So we'll get going here. So, work queues. Getting work stuff in Zephyr. So there's options. You have a lot of options, actually. You have work queues, which includes the system work queue and then the application work queues that you choose to define. So that is something we'll kind of dive into a little bit, is just determining the differences between the two. And then vanilla plain old threads, those are a thing. People use those still. And also, and I touched on this previously in the previous kind of update video. I think I showed some usage of some timers, and we'll just quickly review that again. And so work queues, and specifically, or we'll go into system work queue in a second, but work queues are running off of a dedicated thread. So what is you have a thread running in the background that when you submit a piece of work, you're also submitting a pointer to a function. And you can submit that. It's atomically safe, so you can submit that in ISRs or in threads. It doesn't really matter either way. And what you're essentially doing is you're queuing up this struct of data, which has the function that you want to call, and then just any context around it. And the more context is if you have a delayable work, then that has some extra information to do with it, and we'll get into delayable work in a second. But the important thing to know is that it has its own dedicated stack allocation. So when you're creating, by default, I think Zephyr ships of 1024 or 2048 bytes of stack for the system work queue. You can make that as big as you want, especially if you're using the system work queue in your own application. But we'll get into some reasons why not in a second. So here's actually a visual system work queue. You're going to submit to it. Essentially, you've already created the work, and that gets put into a work queue. And then in the background, that work queue thread is spinning around, and whenever it gets offered a new piece of work to do, the work has been submitted, it immediately, as long as there's time, CPU time, it gets popped off that work queue and goes through the work queue thread where it gets submitted, and then the function call gets called. So here is a very, very basic implementation of this using the system work queue. So we're declaring up at top, and I'll just go here. So we'll go back to the full screen. You're declaring the work. You're declaring the work function. Then you're initializing it. Otherwise, there's no way that the work and the work function get associated together. So you got to initialize it first before you call it, and then you use the k_work_submit to actually submit that work. So that work will get submitted to the queue, and then when it's time to get processed, maybe it's the first in line, maybe there's a couple tasks in front of it. Once it gets processed, first in, first out, it'll get the sum work queue function will actually get called, and then it'll do whatever you want to do inside of it. So along with just the standard work function, you also have a delayed work function. And what happens here is you can actually submit that work to the queue, and what you can do is then you can set a delay for it, so it doesn't have to be operated on immediately. So we're going to, it's not precise, so you're not going to get like exact timing. So that's something to remember, because what's happening is you're submitting the work. The work is going to be actually submitted for processing when an ISR fires in the kernel. The kernel says, "Oh, hey, your time has come. Time to get work done," and then it sends it over to the work queue thread, and then it gets processed on. So similar to the regular K work, it needs to be initialized before use. So just something to keep in mind. So here's this. You can see like the part in the middle there, kernel timer RSR. That's the part that kind of creates that timer or that delay for the work to be submitted. So you can. I find it useful for things that you want to submit, but maybe like a disconnect event. You want to make sure there's a certain amount of time, or even transmission if you're transmitting a bunch of data, and you want to make sure that you've received the ACK or given enough sufficient time to actually do the processing, and then you can create a delay work to do something like that. But it takes advantage of the same work queue. And as I mentioned before, the only context is that you're actually providing some more timer interval information for the kernel to kind of process in that timer RSR. And then here is just a very simple example of how to init and use that delayed work function. Should look very familiar compared to the regular K work. The only difference is you're actually providing, if you look at the K work reschedule function, the reschedule function is very explicit for delayed work. And you can see I'm providing a 500 millisecond value there for this timer or this work to get scheduled at. So, but the same thing for initialization, just a different function. We're just initializing the delayable work instead of just the regular work. But you can see we're using the same work function as before. Now, so here's the differences between the system work queue and maybe say an application work queue. Most of the time, the system work queue is going to be running in the background for various Zephyr operating system tasks. So it's already included. You don't always have to include it, but it's generally used all the time in Zephyr, unless you have a very lightweight application where it doesn't make sense. And one thing you have to make sure is when you're submitting these very vanilla tasks, like if we go back to either one of these delayed work queue definitions, you're going to be submitting to the system work queue. So you have to make sure that you are not doing anything that's going to run a long time, or that it's going to be blocking. If it's going to do any of those, you are probably going to cause your code to panic or lock up, or both. So just something to bear in mind when you are using the system, or when you're submitting work to the system work queue. And by default, it is the kind of lowest application priority, or maybe even a little bit lower. So if it's going to be high priority, it's a high priority task you're going to be doing, you don't want to be putting it into the system work queue anyway. And like I mentioned, both of those previous examples, the delayable and the just regular one, are both using the system work queue. But you can also create as many work queues as you want. You're limited by your memory, the amount of memory you have on your microcontroller. So you're creating it, you're setting the stack size, and then essentially you're creating another thread that processes your own work queue or work items. So here's an example here. I've created a thread stack definition. So we're defining or basically occupying 2048 bytes of stack area size, and we'll allocate that to our work queue in a second. You'll see in a little bit later that we're using the same stack define function for when we're creating a thread. So we're actually just creating the amounts of stack area that's used for the thread internal to the work queue implementation. And also we're just creating a reference to the app work queue. So queue underscore work queue, that is the guy. And then if you scroll down just a little bit, so we'll initialize the work queue. So we're using the name of it, we're using the stack area, we're getting the size of the stack area, we're giving it a priority. So in this case, you have some freedom. You can modify the system work queue priority, but in this case, you can also set this priority to whatever priority you want. If it's a higher priority task, then you can definitely you can change it here, and then you can submit to now this newly created app work queue by using the kwork submit to queue function rather than just kwork submit. And kwork submit by default uses the system work queue, so you need to define what work queue you actually want to send it to. Again, we're initializing the work before it gets submitted. And similarly for delayable, and I don't know if I can put that in here, but delayable has a submit to queue option as well, so you can also submit delayable work to your own custom work queue. So something to keep in mind. So we've been dancing around threads a little bit here, and it is the kind of the basis for all of system work queue functionality, system work queue, and also application work queue. So you can create your own processing logic. You can have your work queue or your threads do anything you really want to. It's going to take its own stack size. So we saw earlier that we're allocating size of a certain amount of the stack to this thread. And you can also very much so, like you saw just a second ago here, is you can assign it a priority. And if we go here, this is just the definition of the thread, and then the function itself that actually gets called, and then you're actually defining using that kthread define macro, and we're just creating the name of it. So the first parameter is the name, second parameter is the amount of stack space you're requesting. The third is that thread function. Some of the other nulls there are just the context, if you want to put some context into the thread itself, depending on your application. And then you can see I'm using the lowest application thread priority, and that's kind of like a built-in macro inside Zephyr. And then finally, in order to actually start it, you have to call that thread kthread start, I believe. And that's just that's the way you get the thread running. And then this thread could be kind of like a one-time thing, or it could be something that runs kind of forever of the life of your application. It really depends. The important thing in here, and I wrote the name of the function, is that it needs to yield. So there are different parts of Zephyr which cause a kind of a thread to yield. You can actually call a yield function, or if you're processing like a work queue or what would it be? It would be a message queue. If you have like a message queue and you're processing that message queue, when that message queue is empty, basically it releases that thread from being used, and then it won't kind of block anything else that's happening on your application. But this is a very basic example, but this is just the way you set it up. You just need to make sure that, again, I've shot myself in the foot so many times because I didn't really understand how the threads work together, and also how to get the data in and out of threads. My preferred way of dealing with concurrency these days is actually mostly creating an event manager, which I talked about in the last video, and handling those events in the main thread, and then sending them out to whatever functionality, different modules inside the code. But there will be always places where if you have MQTT clients, that client is going to be working kind of on its own, in its own space, polling and grabbing data and sending data, along with maybe you have a thread that's used to pull data from like a UART, again, or maybe on a certain interval get sensor data that maybe has to be very timing specific, things like that. You can get creative, but in general, you don't always have to create a thread for something. But if you dive into some of Zephyr's documentation, or even Nordic's examples, like their NRF Cloud client and stuff uses its own thread. The MQTT client uses its own thread. So it's just kind of a good example of creating your own thread and then kind of setting it up for creating for your own tasks. And so and finally, we'll just jump into quickly the timer events. And the big takeaway with the timer is that you're going to be creating this timer, and the kernel will keep track of that time, and it will use the work. It'll use the system work queue to actually execute the function that you're providing it. So as I alluded to before and mentioned before about everything else, is that you got to make sure that these functions, when you're passing them, it's not going to lock up anything, or it's not going to block big, and it's small. It's not going to take a lot of time because you're using the system work queue when these ISR events fire. So just something to keep in mind. So here's a very basic timer declaration. You're going to have that function, and this is the function that actually gets passed to the system work queue for processing. Again, you have this, similarly to the other ones, you have a macro that defines the timer and also associates the timer with the timer function, the function that actually gets called. And then later on in the code, you have the timer start function, which will actually start the timer. In this case, it's a timer that runs every 1 second. So it just fires over and over and over again until you stop it if you want to. And that's, just remember, the biggest thing for these things is just make sure it's not something that's been running so long, and make sure that if you're sharing any data between these, that you're very careful that you're doing it in kind of atomically versus like accessing at the same time. You don't have to worry about it as much with any of these work functions, because essentially only one is going to be working at a time. So I should be clear that nothing is really happening like in parallel, unless you have like a multiprocessor microcontroller. And I don't even know if that's supported in Zephyr at the moment, but you're always going to have one thread running at any one time. It's not like something's going to be running in parallel at the same time. So that's one thing to keep in mind. But generally, you always want to separate your different modules, and if you're sending data, you always want to either put it in some type of atomic piece of static memory that can be used later in a different part of your code. So that's one of the main reasons why I use the kind of the event management kind of paradigm, is because I can create an event in one module. Maybe it's created by a certain thread or work queue or whatever. I can package it up, and then I can throw it over to the main thread or whatever that's going to be processing on the other side, and then doing the same thing from there if I need to send another message over to another module. Might warrant using some type of message queue, or you might be able to call it right from that main thread. So looks like we have some questions here, and I think we're pretty much done with the slides, but you guys have some questions. Hello from Brazil. Hello. Thanks for coming. And then Sonia Mate, hey from Princeton, New Jersey, and hey from Czech Republic. Hey everybody. If you guys have any questions, we have a couple minutes, so feel free to shoot them our way. Otherwise, hopefully that helps. It can get, the biggest takeaway here is that almost everything underneath uses some type of thread. And the processing just happens. That's just the way the processing happens. And the work queues use a thread for all that processing. So as you add an event, it gets processed by a thread. It just depends on which thread you're using. And remember, with a system work queue, you are sharing that queue with other system tasks. You just got to be very careful when you're using it. Looks like a question here. So when the timer hits the handler and is added to the worker queue, so there will be more latency from the queue itself. Yeah, it's very possible that there's going to be a small amount of time. There's going to be time between the ISR firing, it getting queued up, and then it getting processed. So say if it's going to the system work queue, there might be other tasks in front of it. So queues are usually first in, first out. So if there's a couple items in place already, then it's going to run through those first and then get to the one that was the timer event. You can get around this by using something more like a hardware timer, where you're actually firing an ISR and you're doing that work in an ISR, or creating, what I'm saying is you're going to use that ISR to do anything that's time critical. and generally all the stuff that I've said here is generally not time critical. It's if you do need time critical, then hardware timer. Cool. Well, I hope this helped you all, and if you have any other ideas for future content, please let me know. And of course, I'm going to ask everybody to subscribe again. And we'll see you next week. Let's see. Yeah, and I'll try to figure out what to go over next. But thanks for coming, and I'll see you on the next one.